Hello everyone. Today I'm going to talk about my work on improving automatic program repair by using bug reports and tests together. Automatic program repair techniques typically start with a buggy program that fails on at least one test and use an off-the-shelf file localization techniques to produce a ranked list of suspicious program statements that are likely to cause a bug. Next, for each ranked statement, repair techniques iteratively generate and validate candidate patches that could potentially fix the bug. If successful, techniques report the patch as a plausible patch that passes all the tests. Often repair techniques struggle to patch defects, and even when they do, when developers manually inspect the plausible patches, they find that the patches often overfit the test suites used in the repair process and are not actually correct. Recent studies show that one of the main causes for this patch overfitting problem is the imprecise file localization that puts the buggy statements lower in the ranked list, preventing repair techniques to patch actual buggy statements. In this study, we attempt to address this localization error problem in program repair. Our key insight is to use natural language bug reports in addition to the test suites to improve the file localization accuracy. For this, we developed BLUES, which is a first unsupervised statement level bug report based for localization technique, and RAFL, which is the first unsupervised approach to combine the results of multiple for localization techniques. We use our RAFL approach to combine the results of BLUES with an existing spectrum-based for localization technique that is popularly used by many test suite-based program repair tools to develop SBIR, which improves the file localization accuracy and thereby improves program repair. Ours is a first investigation of simultaneously using multiple software artifacts to improve program repair. Now, before I tell you how our techniques work, let me show you how using SBIR improves program repair. To analyze the effect of using SBIR in program repair, we selected three modern repair techniques: RJA, SequenceR, and SymFix that employ diverse repair algorithms and exhibit varying sensitivity to the file localization accuracy. We customize these techniques to use SBIR as their file localization strategy and compared their performance with 14 existing repair techniques as well as their own prior evaluations on the defects4j benchmark. We found that using SBIR enabled these techniques to correctly repair 7 new defects that 14 existing repair techniques could not fix. Further, using SBIR also enabled these techniques to correctly repair 7 defects that they themselves could not fix earlier using SBFL. Thus, using SBIR enables repair tools to correctly patch many new defects without modifying their patch generation algorithms. Next, we analyze the effect of using SBIR on the quality of repair tools when using different file localization strategies. Of the three repair tools we consider, for our job, which is most FL sensitive, we saw 33% improvement in the number of defects it correctly patched when using SBIR than when using SBFL. For SequenceR, we saw 20% improvement, while for SymFix that uses tricks to address imprecise file localization, it patched the same number of defects using SBIR and SBFL. Thus, using SBIR significantly improves the quality of more FL-sensitive repair tools. Finally, we analyze the effect of using SBIR in reducing the localization errors. For this, we computed the maximum number of defects the repair tools can correctly patch using any of the file localization strategies, including the perfect file localization, where repair tools use only the actual buggy statements to produce patches. We then compared the number of defects that could not be patched due to the localization error when using different file localization techniques. As shown, using SBIR lowers the localization error by providing repair tools an earlier opportunity to patch actual buggy statements. Now let me tell you about how our BLUES, RAFL, and SBIR work. BLUES takes as input a natural language bug report and source files of a project and outputs a ranked list of suspicious program statements. BLUES is built on BlueIR, an existing technique that uses structured information retrieval-based approach to rank suspicious files. In step 1, BLUES extracts the terms associated with the natural language summary and description fields of a bug report, performs operations such as camel case splitting, stopword removal, and stemming, and creates an XML-based bug report query as shown on the right-hand side in the slide. In step 2, Blues parses the abstract syntax tree of the source files and extracts the terms associated with the class, method, identifier, and comment fields of the source file AST and creates an XML-based document corresponding to each source file as shown on the slide. In step 3, Blues uses the BM25 Okapi information retrieval model to compute the similarity between the bug report query and source file documents, executing the model 8 times for each combination of bug report fields and source code fields. The final rank list of source files is obtained by summing up the similarity scores that looks like this, where each line corresponds to a unique source file. Next, Blues parses the abstract syntax tree of the rank source files to extract 57 kinds of AST nodes and create a statement document collection. For example, if we consider the topmost file in this rank list, which is faststateparser.java, Blues extracts the terms associated with the if statement node and the conditional expression node on line 308, and it creates XML-based statement documents as shown on the right-hand side. Blues then executes the same IR model 2 times, once for each of the summary and description fields of the bug report, to compute the similarity between the bug report and statement documents. Blues then sums up the similarity scores to produce a rank list of suspicious statements that looks like this, where each line corresponds to the unique source file, line number, and AST node number. In the final step, Blues combines the scores of the ranked files and statements to obtain a final rank list of suspicious statements. For this, Blues provides a ranker module that uses user-specified configuration parameters to combine the file and statement scores. Comparing Blues for localization performance with iFixR, a bug report-based repair technique that internally uses supervised statement-level for localization on 171 defects and defects for J, shows that Blues consistently localizes more defects for lists of size 25 or more, as indicated by hit at K values, and ranks buggy statements higher in its list as indicated by exam scores. Comparing the performance with a baseline that does not combine the statement and file scores also shows that Blues consistently localizes more defects and ranks buggy statements higher in its list. Thus, for scenarios relevant to program repair, Blues consistently outperforms the state-of-the-art and baseline. Next, to combine the IRFL-based Blues with SPFL-based OCHI, which is popularly used by many test suite-based program repair tools, we developed Raffle that uses rank aggregation algorithms to combine the results of multiple for localization techniques and produce a super list that is as close as possible to the individual lists being combined. The key idea behind Raffle is to define an objective function that encodes the weighted distance between delta, which is a combined list of size k, and individual rank list Li. The goal of Raffle is to find an optimal combined list delta star that minimizes this objective function. To solve this optimization problem, Raffle implements two algorithms, cross-entropy Monte Carlo algorithm and genetic algorithm, and provides two distance functions, Spearman-Foot rule and Kendall-Tau. For details of these algorithms and distance functions, I invite you to read our paper. We use Raffle's cross-entropy Monte Carlo algorithm and Spearman-Foot rule distance to develop SPIR that combines the results of OCHI with Blues. To account for the randomness, we compute SPIR using 10 random seeds and compute the mean, standard deviation, and coefficient of variation while evaluating SPIR's performance. Comparing the SPIR's for localization performance with its constituent techniques SPFL and Blues on 815 defects and defects for J shows that SPIR consistently outperforms SPFL and Blues for all values of K, corroborating existing research on combining for localization techniques. Comparing the SPIR's for localization performance with 9 standalone for localization techniques on 334 defects and defects for J shows that SPIR outperforms all the 9 techniques. And finally, comparing the for localization performance of SPIR computed using our unsupervised Raffle with the SPIR computed using supervised rank SVM on 815 defects and defects for J shows that using Raffle significantly outperforms using rank SVM, which is used in many state-of-the-art combining for localization techniques. To recall, I already showed you how using SPIR enables program repair tools to correctly patch many new defects. It improves the quality of more FL-sensitive repair tools, and it lowers the localization errors. To summarize, I presented to you BLUES, the first unsupervised statement-level bug report-based for localization technique; RAFL, the first unsupervised approach to combine the results of multiple for localization techniques; and SPIR, that uses RAFL to combine BLUES with OCHI. And the evaluation of BLUES, SPIR, and how using both bug reports and tests together improves program repair. With that, I'm up for questions. Thank you all for listening.